Okay, in this example, we're going to focus a little more on turning points than we did in the previous video. We're going to first find the intervals where this cubic polynomial function f of x is increasing or decreasing, and then we're going to determine the exact coordinates of every turning point. So it goes without saying, there's a linkage between these two items. You can't determine turning points until you deal with your intervals of increase and decrease for your function, which means you also, of course, have to find your first derivative, because that's how you're going to know if a function goes up or down, depending on its sine of its tangent slopes. And you have to find the critical values for your function before you can do your Sine test to determine your intervals of increase or decrease. So we got lots of work to do, is what I'm saying. First things first, we have to differentiate our function and get our first derivative. So this derivative actually might look bad, but it's not. It's just a polynomial function. So 3 comes down, wipes out the coefficient of the thirds. We're just going to be left with x squared, our first term, and then differentiating x squared is minus 2x. I guess 2x after the subtraction, and then differentiating minus 3x becomes the coefficient, and differentiating 5, no point in writing that, that is 0. So we need our critical values, and the logic is we need to know where this first derivative is equal to 0 if we have any hope of determining when it's going to be negative or positive, because 0, of course, is the tipping point. And that's also, we can call it a little more technical term. We can refer to this as looking for the critical values of this function. So still very doable. This is a quadratic expression, this first derivative obviously. So if I try to figure out what makes this quadratic equal to 0, I'd be a fool if I didn't try to factor this. Be a fool if I didn't actually successfully factor this. So x minus 3, I'm putting too much pressure on myself now. X minus 3 times x plus 1 equals 0, and it looks like we have two critical values. So we'll say the CVs, these are 100% definite critical values. Whatever makes this 0, it's going to be maybe in ascending order, -1 and +3, which means there's two potential turning points in this function. And again, not a very mysterious function here. A cubic polynomial can have up to, remember, n minus 1, or the degree of your polynomial. So this would be have up to 3 minus 1 turning points. So we don't have evidence yet that we have turning points, but we have evidence that we have two stationary points. And if the function turns around at those stationary points, we can call them turning points. So let's move on, and we'll do our sine test next on the number line. Of course, that goes on forever. And I'll label that as our first derivative, because this is displaying the signs of our first derivative, and I'm not really putting a whole lot of tick marks on here. I'm just spacing things out a little bit. As long as the two critical values are on our number line, we're good to go. So now we have to test, and the first thing I always test is 0, because it's hard to screw up, and 0 is between -1 and 3, and if I plop in 0 into my factored form, I should add, is a lot easier to work with. We get -3 times 1, so that looks like a negative. So our first derivative is negative in between -1 and 3. And double check, because you don't want to obviously make a mistake, especially this early out of the gate here. So if I put in x equals 0, yeah, -3 times 1 is negative. And I'm not sure if you need to do this, but if you feel the need to do something like f prime of 0 is less than 0, if that helps you understand why there's a bunch of negatives above that number line, go for that as well. Okay, maybe to the right of 3. Something like 4, 5, 6, and then we realize we're going to have a positive factor multiplied by a definite positive factor. I notice I'm not really calculating anything specific. I'm just checking to see, are both of those factors going to be positive? And if they are, then of course I know my first derivative is going to be positive. If you don't like that and you feel that's a little wishy-washy, then just put 4 in, for example, and get 4 minus 3, which is 1, multiplied by 4 plus 1, which is 5, and then you can figure out that your tangent slope is actually, I guess, 5 in that case, but it really doesn't matter what it is. You're just trying to pinpoint the sign on your tangent slopes to the right of that critical value 3. So one more. something to the left of -1, and we'll put -2 in. And if you're having problems following me here, maybe I'll just substitute a -2 in here into my factored form of my first derivative. So -2 minus 3, -2 plus 1, and I'm saying to myself I got a negative being multiplied by another negative, so this has to be positive. If you'd prefer to say -5 multiplied by -1 and say to yourself, oh yeah, that's plus 5, well, that works as well, as long as you know that your first derivative is positive to the left of -1. So some scrap work there. Now I guess I should write out my intervals. Remember I said in the last video, writing out intervals is kind of a nuisance when you're trying to use those intervals to determine something else, in this case turning points and what they are. But I guess we can we'll write them out, of course, because I want you to be, I don't hate for you to be losing part marks on an actual assessment because you failed to write down your intervals, because then you could blame me if I don't do it in this video. So before we do that, I'm just going to say we have an increasing function to the left of -1, since all those positives, of course, correspond to positive tangent slopes. Then we have a decreasing function. And then we're back to some positives. Then we have an increasing function. And remember, try to avoid those critical values when you're talking about increase or decrease, because if the tangent slope 0, the function is absolutely stationary there and standing still. So if we see a function going up, then going down, then going up, it's pretty clear to me that we have 2 turning points. Okay, so we'll deal with that separately. I'm going to write out these intervals. You can see I'm kind of procrastinating. It's kind of a nuisance, but if I don't do it now, I will forget. So let's just say from left to right, f of x is increasing. Over x belonging to an open interval from -infinity, not including that, of course, up to, but not including the critical value of -1. And I'll just write down the other ones here quickly. Okay, so there we are. We got our intervals written out with the magic of technology. Didn't have to wait too long for that. So let's turn our attention back to our turning points here. I think it's obvious with our function going up and then down and then up, it's zigzagging, so it's changing directions. Add x equals -1 and 3 from our number line. If that wasn't enough, you got the written version of it there in yellow as well. So I've seen enough. We have 2 turning points here, and that's not just because the first derivative was 0. Of course, that's all that means is that we have stationary points, but we figured out that due to the changing direction of the function at x equals -1 and 3, that those stationary points are turning points. So let's write them up here. So we'll say, therefore, f of x has, I'd like to say TPs, but let's write it out on our first example at least, has turning points at, we'll write the coordinates. Unfortunately, we can't just list the x values because they want the exact coordinates, or I guess I want the exact coordinates since this is my madness here. And that's a little bit of a madness because now I have to figure out what my y value is for that function when I input -1. So you might just turn to a calculator there if you're smart, or lazy, maybe both, and then put 3 into your function as well. Okay, so this is annoying, but this will be my scrap work here. We'll get through this quickly, and definitely check this with a calculator. This could go horribly wrong for no reason other than maybe rushing too much. So 1/3, if I put in -1 in there, it's actually going to be -1/3. And then when I put a -1 into the square, we'll get a minus +1, and then we'll get a +3, then we'll get a +5, and it looks like I have a 7 minus 1/3, which I'm going to say is 6 2/3, and we'll definitely check that on Desmos, and maybe you've already checked it on your calculator there. If you're shouting, yes, you got it, appreciate it, I can almost hear you. Yeah! And then unwisely, we'll do this by hand one last time. If we put 3 into that f of x and figure out f of 3, we get 3 cubed, which is 27, and 1/3 of that is 9. Minus a 3 squared, We got another 9. We got minus 3 times 3, and then we got a plus 5. So I guess we can get rid of those and say that's a minus 4. And let's have a visit to Desmos, and we'll fact check my arithmetic here. Okay, pleasantly surprised my arithmetic actually held up here in the waning moments of this video. Just go through to make sure we know what those turning points are, what we found and where those turning points are. Of course, you can probably see them on our graph, but I think most importantly, this intervals business of increase and decrease. I think you can see here that our tangent slopes are positive, pretty steep, by the way. Very steep. My computer's getting cranky. They're still positive, and then boom, flat lines. That's a turning point, and then our function starts to come down, which is what makes that a turning point. Our function just doesn't stop and say, you know what, I'm going to keep moving up. It's going to turn around, and notice we have negative tangent slopes all the way until it peters out again. They become less and less and less steep, but they eventually go from negatives back to a 0. And our function decides not just to keep going down after that stationary point. It actually turns around. So you can see your tangent slopes are telling the tale of 2 turning points. Positive tangent slopes petering out to 0. Then the negative tangent slopes petering out to another 0. If I can get that to stick, there we go. And then positive tangent slopes again. And that's what makes those turning points. Okay, I think that's good enough. And one last thing, I think it's obvious that's maybe not enough to call that a turning point. It's actually a maximum value, but not everywhere. If you can see over here, my function has already beaten that maximum value of 6 2/3. So we call that a local maximum value. Right? And then down here, we call that a local minimum value, because over here to the left of my over to the left by my white horizontal line, you can see that function is already going smaller than that local minimum value of y equals, or f of x equals -4. So refer to those as max and mins respectively, those 2 turning points. And maybe we'll just double back to our written work there quickly, just to make sure how you can see that if you're not using graphing technology as well. Okay, so back here, gave myself a little more elbow room. I like to just think of those positive, negatives, and positives as, well, not just think of them, what they really represent are tangent slopes. So if you want to write some kind of a positive tangent slope, all right, it doesn't have to match anything specifically, as long as you draw a tangent line that says a positive slope, that does the trick. And then right at -1, we know we have a horizontal tangent, although that doesn't really look it, but I think you get the idea. And then after that, our tangent slopes get negative again. And I think if you look at the contour up here, you can probably visualize a local maximum, even though that's an absolutely horrible contour. Technologically challenged here, at least in terms of artistry. There we go. That's a little bit better, even though you can't see the tangent slopes anymore. So you can see that it makes a lot of sense that we call that a local max. And that's because if your function goes up and then goes down, well, guess what? It has to be a local maximum value. So we'll worry about this more in future videos. But for now, just in the waning moments here, just quickly keep in mind that it's not really enough to refer to these things as turning points. It'd be nice if you go the one step further and just trace out what your tangent slopes are doing, and it becomes pretty obvious that this has to be some kind of a maximum. And notice I'm choosing to say it's a local max, because we know our cubic function can definitely beat that 6 2/3 y value once we, especially when we start going farther to the right. And then similarly, and I learned from my mistakes there last time, if I draw a contour first and then try to put tangent slopes on it, I think I'll have a little more success. If we have tangent slopes that are negative, and then right at +3, we have a horizontal tangent, and then they go to positives again. Yeah, I think it looks like it has to be a minimum value that we have there, tracing out a smiley face in that case. Okay, that's more than enough. We got our intervals, we identified our stationary points, showed that they have to be turning points here, and then we looked at Desmos. And then if that wasn't enough, we doubled back to say, you know what, you don't have to rely on Desmos if you want to go one step further to actually classifying your turning points as either local maximums or local minimums.